take a look at the notes and we'll continue on. The homework for today is, now hang on. The homework for today is the 3s and the 4s. The 3s and the 4s and a demo afterwards. So, and unfortunately you will not do a lab with the demo equipment, but in AP next year we'll be doing some labs. Let's talk about, hang on, let's talk about strong acids and bases, and I know you already have the blanks here, so I'm not too concerned about that. But when we talk about strong acids and strong bases, what I don't want you to do is be like everybody else that hasn't had chemistry and they hear the term strong acid or strong base and they go, ooh, those are really bad. Well, if I take a strong acid or a strong base and dilute it down, we could pour it all over ourselves and be just fine. Strong doesn't mean that it's harmful. Strong means that it dissociates completely. So if I have something like hydrochloric acid, stuff that you put in your swimming pools or stuff that you use to kill bacteria and everything else that's fun, if we dilute that down enough, it's okay. However, if I take something that's weak, which doesn't dissociate very well, and have a high concentration of that, it could hurt me. All right. So strong and weak don't go along with what we think about as being something being strong, which could be bad or really harmful. It just means it breaks apart completely. That's all it means. So don't freak out when you see strong. And the nice thing is when you take AP chemistry, okay, when you take AP chemistry, there's only 6 strong acids that we need to memorize, and then the rest is weak. So it's pretty simple. Water can break down into hydrogen ions and hydroxide ions. Because we have that knowledge that water can break down into hydrogen and hydroxide, then water can act as either an acid or a base. And we talked about that, I think, yesterday. And we also have this little constant. It's called Kw. We won't be doing anything with the Kw in here, but in AP we'll use it. But we will do some calculations with this. And it's pretty simple because what you have are 2 variables, and then you have a constant. So the hydrogen concentration times the hydroxide concentration equals 1.8 times 10 to the negative 14. So it's just a matter of using your calculator to determine the unknown. I would give you one of the 2 and then ask you to solve for the unknown. So it's not too bad. Really important, if you have an acidic solution, what that means is you have more hydrogen ions than you do hydroxide. If it's a basic solution, you have more hydroxide than you do hydrogen. Okay? If you want to put a star next to that, highlight that. That's some good information. You'll see it on the homework tonight. Okay? So if you have a hydrogen concentration that's pretty high versus a hydroxide, hey, you got an acidic solution. So let me give you a little pop quiz here. Let's see how good you are. You love pop quizzes, right? You're doing pretty well. Here, let's say that we have a hydrogen concentration that's 5.55 times 10 to the negative 9. And I'm just making these values up, so don't freak out. And let's say that I have a concentration of 7.77 times 10 to the negative 3. Is this solution acidic or basic?
Basic.
I'm hearing 2 answers, acidic and basic.
Basic.
Yeah, it's basic.
It's basic?
No. Yes.
No?
Yes.
Yes?
No. Yes.
All right. So everybody in here is saying that this value here is greater than this value here. Negative 9's good versus negative 3. So you don't look at how big this value is because that's actually pretty small. So in this case, the hydroxide is greater than the hydrogen. Therefore, this is a basic solution. Okay. Got it? Let me give you another one. See how good you are. Say we have a hydrogen concentration of, I don't know, 3.33 times 10 to the negative 8. And hydroxide has a value of 7.98 times 10 to the negative 10. Acidic? Does everybody agree? Good. So the hydrogen concentration is higher than the basic concentration, or the hydroxide. Okay. So acidic. Example of showing how we're going to do our homework, and I'll do one of the homework problems if you're quiet here in a second. Weak acids and weak bases. Pretty simple. Weak acids and weak bases do not dissociate 100%. Okay. Strong do. Let's take a look at one of the homework problems. The threes are part of your homework, so let me take a look at one of those. What is that?
So wait, we're not doing the practice problems?
There isn't a practice problem.
Yeah, there are.
Oh, there are.
No, there
Oh,
aren't.
cool.
No, there aren't. We can do the homework.
Nope. You're right. Thank you. Yeah.
Sorry.
You're so good. Kelsey.
Okay, you still have to do one on the homework.
Yeah, we still could. Not now. All right, number 5 at the bottom of page 7. The question asks you to calculate the hydroxide concentration if the hydrogen concentration is 7.45 times 10 to the negative 6. Then indicate if it's acidic or basic. Guys. So again, the equation that you'll be using looks like this. Write small. Okay. So that's the equation that you'll be using. To rearrange it, you know that the hydrogen concentration, and again, this is information that you don't have to write down. Copycats. Okay, so that's given. So if I know that I know the hydrogen and I know the constant, I'm looking for the hydroxide. So how would I rearrange it so I solve for the hydroxide? Very nice. And 1.0 times 10 to the negative 14 will always be on top. Everybody hear that? 1.0 times 10 to the negative 14 will always be on top. And since we know our hydrogen concentration, we'll put it right down there. So it looks like that. And that's equal to 7.45 times 10 to the negative 6. And then make sure your calculator can get you a good solid number here. What's that? Depends on how you use it. If you use your scientific calculator well enough, you won't have to use parentheses. But if you're not sure, then I would use parentheses. So 1.34 times 10 to the negative 9. I want to make sure that you can type this in. That's why I'm having you do it. Thank you. What's the matter?
Oh, that's my correct.
You got a bunch of zeros? Bring it over here.
I got the same thing as you. Really?
Why?
Okay.
Okay, then hold your
Now hang on. Here is, whoa. All right. Here is what this calculator got. Okay. Now listen. Sit down. What you need to do if you get something like this, then you actually need to go to scientific notation. Do that by hitting second, and then this button here, which says psi, whatever, go 1 over, and you'll get the same number that I got. Okay. So second, this button, and then scoot over. So second, that, hit psi. All right, try the next one on your own, number 6. Don't peek up here. You got that?
I got that.
Good.
Same here.
All right, number 6. Do that one on your own, no peeking.
How am I supposed to do this thing?
You should, let me see it. Bring it over here. I bet I could get you on a
Wait,
Start
Would
this.
number 5 be acidic or basic?
Oh, yeah. Thank you.
You're welcome.
To answer this, whether it's acidic or basic, so the hydrogen concentration is this, the hydroxide is this. Is this acidic or basic? Again, this is from number 5 practice problem. My hydrogen concentration is this, my hydroxide is this. Is this acidic or basic? Acidic? You're saying this is higher than this? It is acidic. Very good. Well, let's see.
That's what I got. I got 5.8.
Wake up. Is that what you got?
Yes, that's what I got. No, what did I do wrong?
So is this acidic or basic?
Basic.
Very basic. Okay. This is a very low concentration. This is a very high concentration. Okay. We talked a little bit about neutralization reactions. Now listen. We talked about neutralization reactions last topic when we did the ionic equations and anionic equations. And generically speaking, what we're using when we do a neutralization reaction is you have an acid reacting with a base, and we're forming a salt and water. Okay, so this is something that we've already talked about. Okay, so however, to determine what our pH is, we can do some calculations, and I think we'll use, don't worry about that evidence for, I'll come back, hang on. We're going to use this calculation here where it talks about the volume of the acid times the molarity of the acid is equal to the volume of the base times the molarity of the base. So when we are looking at a neutralization reaction, we're interested in getting it to this point, because when we have equal amounts of acid with equal amounts of base, and I'm talking concentration and volume, then we have a neutral solution, also known as an equivalence point, which I thought I had listed somewhere. Might be somewhere else here. Talks about neutralization. Neutralization and equivalence point represent the same thing. And the bad news is, in AP chemistry, we spend about a month and a half going over the stuff that we're spending 3 days on. So we're barely scratching the surface of acids and bases in this class. However, I want to make sure that you have a very brief overview of what's going on here. Now, even though we have some opportunities that we could have some insoluble salts, I will not give you any of those types of things. So all the salts will actually be soluble, because I don't want a dirty salt and water type solution here. This one's kind of a goofy one. How are you going to be able to tell if a reaction is exothermic? Not see it,
Feel it.
feel it. Okay. Yeah, that's all right. When we talk about a neutralization reaction, what should our pH be around? 7. Very good. We haven't talked about the pH scale. What does the pH scale generally start at? 0 and goes to 14. Okay, it goes from 0 to 14. Now, we can have some values that are greater than 14. We could have some values that are lower than 0. But for this class, we'll keep it between 0 and 14. All right. Defining neutralization, that's actually when we have the same number of hydroxide ions as we do hydrogen ions. Okay? When they're equal. And did we say that at neutralization the pH was 7? Okay. Complete neutralization, in some cases we could use an acid that is considered a polyprotic. What does poly mean? Many. So when we look at things like phosphoric acid, sulfuric acid, things that have more than one hydrogen that could dissociate, that's a polyprotic acid. If I'm looking at a monoprotic acid, the type of acid that I'm going to use today, it only has one hydrogen to dissociate. Mono meaning one. The protic means that it's a proton. In other words, when you look at a hydrogen ion, it only has a single proton, no electron. So we call it a hydrogen ion, but really it's a proton. Titration, that's what this apparatus is. It's set up. And what we use this for primarily, and if you take chemistry in college, you'll use this for a couple labs. We'll do a couple labs next year in AP Chem using that. But it's a process, a lab process, that helps us determine one of these variables, okay, which is kind of nice. So when you're working these problems out, you'll have 3 of the 4. And typically what we'll be doing is we'll be looking for one of the molarities, whether the molarity of the acid or the molarity of the base. And again, here's that equivalence point or end point. These all represent the same thing. That's when we have the same number of hydrogen atoms as we do hydroxide ions there. Indicator, we talked a little bit about what an indicator does. An indicator helps us to indicate when we're at a desired pH. The indicator that we're going to use today is phenolphthalein, and it's kind of a neat one. You'll like it when we put it in there. And an indicator is really neat because it'll show up for a moment and then it'll disappear as the solution mixes. Because what we have is, as we introduce hydrogen ions to the solution, then it reacts with the indicator and causes it to disappear. But when the solution becomes super basic, then it becomes a color, which you'll see here in a little bit. Here's an example of how to use this equation. It's probably one of the easiest ones. It's just like using P1V1 is equal to P2V2. So you'll have 3 to the 4, rearrange it, and then plug and chug. You like that, right? Here's an example problem that's already been worked out. Let's see if I have another example problem. I do. Look at that. Let's take a look at these example problems. Second hour was so nice that they didn't even tell me about them. You guys are the good class, I swear. All right, let's look at number 7 here.
I'm sorry.
No, Kelsey, you're a good kid. It's on the record. All right, number 7 says, when 42.5 milliliters of a 1.03 molar solution of sodium hydroxide. Now let's stop right there. The equation that we're using is the volume of the acid times the molarity of the acid is equal to the volume of the base times the molarity of the base. Okay? Looking at our first two things right here in the beginning of the sentence, what does 42.5 represent? Volume of who? Base. It ends in H. If it ends in H, it's a base. If it starts with an H, it's an acid. Okay. Now, a lot of the bases that we're using ends in hydroxide, but it still ends in H. So we have our initial concentration, this is our volume of the base, and this is our molarity of the base. Okay. Then the question goes on, it says, has added 250 milliliters of vinegar, a solution of acetic acid, which is written there. So the 50 milliliters here represents what? VA. Okay. Then blah, 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 blah. Calculate the concentration of acetic acid. So what we don't know is that guy right there. So when we rearrange equation, let's get VA over here. So the equation looks like this. Then just plug in your variables. Now, you don't have to change the volume unless you're just dying to. Since they're the same, milliliters, we can leave it as is. Okay? We don't have a constant that guides us to tell us that, hey, you need to get that to liters. You can just leave them alone. But don't mess them up. That's why I like to write the variables above. So we have 42.5 milliliters, and then the molarity was 1.03, and then we have 50 milliliters.
Where did you get 1.03?
Right here. And then just solve. Plug and chug. Easiest thing to do. So around 0.8, we'll say 876. How's that? Okay, and that's molarity. So the concentration. Try that next one on your own. Don't peek up here. Man, I gave you a lot of room to do that one. What the heck? Oh, something's wrong with me. I apologize. I'd like to get you guys into a pattern here. So the next practice problem says calculate the volume of a 2.55 molar HNO3, an acid. Wonder what that is. Needed to neutralize 67 milliliters of barium hydroxide, a base. Now I should have given you some more stuff. Uh-oh, we're missing something. Let's say that we have a, for our, let's say that that's a, let's say it's 5.0 molarity of the base, because you have to have 3 of the 4. Okay. So here's our addendum. 5.0. Yeah. So we're looking for, yeah, I don't know, it's right there. This one you're working at on your own. And change this not to barium hydroxide, not that it matters. Let's make that sodium hydroxide. Because if it's barium hydroxide, we have to do something else to that. So 5 times 66. So around 131. Okay.
Do we not take it out?
3 sig figs. Yeah. All right, and the homework, the 4s. Now let me see, make sure that they're good here.
Craig, can you put that work back on?
Okay. And then, while you're doing that, we'll get the titration set up.